Astrophysics, the study of our universe, can feel detached from our lives here on Earth, but it doesn't need to be. Here in Potsdam, we've recently hosted a large conference with researchers from around the globe. In the process, we've asked some experts to break down key astrophysical concepts, from galaxies to cosmology. In this third episode, we'll meet Dr. Pengfei Li and Dr. Yanbin Yang. They'll discuss dark matter, an invisible material that shapes the evolution of our universe.
Hello, I'm Pengfei Li. I'm a Humboldt Fellow at Leibniz Institute for Astrophysics at Potsdam. I study dynamics of galaxies and galaxy clusters and use that to try to constrain the nature of dark matter and testing different dark matter models.
So my name is Yanbin Yang, and I'm working at Paris Observatory. So my current research interest is dynamics of galaxies. Currently, I most focus on the galaxy in the local group. I'm also interested in dynamics of galaxy formation of spiral galaxies, for example.
Okay, astronomers believe dark matter exists for a lot of reasons. Historically, the first reason was suggested in galaxy clusters, which is big cluster of many galaxies, and people estimate the total mass based on the galaxy kinematics, basically how fast they could move, and they found the total mass is much larger than was observed, the visible mass. So they think at that time was still unsure, so people think there must be some invisible mass. So later on, the study of disk galaxies, which is pretty much similar to our Milky Way, so which present a thin disk, is like a plane. So we can measure how fast the plane rotates. So that tells us the total mass we need to support such a rotation. However, given the mass is constrained with small range, so from our understanding based on Newtonian gravity, so we would expect the velocity decrease at larger radii. But what we see is the opposite. We see the observed rotation velocity remain almost flat to a very large radii. So those evidence make people think there must be a much more extended mass distribution that has not been detected yet.
So this is basically the nature of the dark matter. Is actually the unseen matter is we don't detect, we don't see it directly. It is out of any detection instrument method that we have currently, but we don't know what is missing. So basically, for astronomers, the dark matter means the matter not detected, not seen, but it is expected from the Newton dynamics, from the rotation curve. There's evidence for missing matter, which we rephrase it as dark matter.
Regarding what is dark matter is still in debate, unsure, because we have not detected it yet. Until we detect it, we cannot say exactly what its properties. But there are some astrophysics constraints which provide many hints of what dark matter could be. So like, first, these should not interact with the photons very much. Otherwise, we would have observed them. They do not emit photons or reflect photons. That means they do not interact with the photons. This is the very first property that people know about dark matter, if they exist. From cosmological considerations, dark matter cannot be baryons, the normal matter we can see that makes the stars, galaxies, and our human being. The other property is about the mass of dark matter particles, which we usually call cold dark matter, warm dark matter, or hot dark matter, depending on their mass. If their mass is very, very low, which means they are hot dark matter because they move very fast, close to almost relativistically, so they appear very hot. But if they are supermassive, then they're very heavy, and they move very slow, so they appear to be cold. So we call it cold dark matter. These different types of dark matter, based on their mass, lead to completely different models of galaxy formations. The widely accepted model is called cold dark matter model. This is because cold dark matter models can form more smaller structures like dwarf galaxies, while struggling for warm dark matter to form dwarf galaxies and ultrafaint galaxies. Dark matter particles, as they have mass, so they are gravitating. They are not uniformly distributed in the universe. That means many dark matter particles are clumped together to form some small structures, what we call now dark matter halos. Even before galaxy formed, so the primordial halos should exist, as they do not interact with photons or baryons. So in the standard model of galaxy formation, dark matter halos play a critical role in forming galaxies, as they set the very initial seeds to accrete baryonic gas to form current galaxies. Because at a very early universe, the radiation dominates, so baryonic mass are closely coupled with photons, so they cannot clump together to form any galaxies. So dark matter halos, since they do not interact with photons, so they can clump together to form the primordial halos, which form a strong gravitational potential wheel, which help gas accretion. So in this step, the baryonic gas can be quickly accreted into the center of dark matter halos and form the currently observed galaxies.
Dark matter halo for spiral galaxies is important. Let's say, let me rephrase it, we need a more or less spherical distribution of the potential of the halo to stabilize the disk, to avoid giant bar formation in the disk. That means if you have no such spherical distribution of matter, all the spiral disk galaxy will form a bar inside quickly. But this is not observation tells us. For me, this is one of expectation that we are thinking the missing part, perhaps spherically or roughly spherically distributed. This is the shape you can infer from the property of spiral galaxies. On the other hand, when we talk about halo, subhalos, is more or less a concept coming from cosmological simulation, starting from lambda CDM, called dark matter simulations. And in that simulation, you predict a huge number of subhalo and the property of subhalos. For the moment, again, so this is we're lacking of direct detection of such properties, particle or what is a dark matter. We're lacking of direct measurement of that, so we don't know. There are a lot of things is moving. Look at history, things are always changing, right? I mean, the rule is changing, is not static. For example, about LMC, in 2013, HST released the first proper motion measurement of LMC. It changed completely understanding of LMC system. Before the epoch, people were assuming we don't know proper motion of LMC on sky, and we assume it is bound to the Milky Way. But when the HST proper motion comes out, it tells you that, I mean, on the sky, the object, I mean, LMC is moving 350 kilometers. Everybody shocked. And now, just a few years later after that, all the community accept that LMC is in the first info. Whatever the Milky Way mass is, it is the first info. It completely changes the scenario. So maybe there's a surprise in the future. There's so many fantastic instruments, space satellite telescopes, etc., Gaia. Perhaps in the future we'll have super Gaia. It will change completely, so open. You can find me by searching my name, Yanbin Yang, and
You can follow me on Twitter at Pengfei Li 0606.